Okay, now let's see how we can actually find out the change in enthalpies between two temperatures. So you have the delta H at one temperature and you have the delta H at another temperature. How do you find the difference between the two using the Cp? So we start with this equation, which was basically equation 31 that we saw earlier. So we start with this and we rearrange this by taking the dt to the other side. So this becomes delta Cp at the temperature, right? So we do this dt at the temperature. So we just took this dt to the other side. Now what we do, we integrate this from the delta H that we want. So we had a delta H at T1 and we went to the delta H at T2. So this is the difference that we want. To do this, we basically went from the temperature T1 to temperature T2. Now how do we simplify this? It's simple. The integration in here will give you the delta H of T2 minus the delta H of T1. On this side, you get the delta of Cp dt of T1 by T2. So this remains the same. Now, what we have to do, so if we want to calculate we want to calculate the enthalpy change from temperature T2 and temperature T1, we need to find out Cp, the delta Cp, as a function of temperature. Now, how this can be done? How can you find out Cp as a function of temperature? This can only be found out experimentally. So you do experiments. You actually conduct experiments and you raise the temperature and you try and find out the Cp. Okay, so you have Meyer-Kelly equations in which you actually. So what we do is we try and get temperature versus Cp plots, and then say you got these are data points that were generated through the equation. Now, mathematically what we do is we then fit a polynomial equation to these data points, right? So Cp becomes a function of temperature, right? Cp becomes a function of temperature. Now, using a modification of this, so this is the Meyer-Kelly equation. So whatever equation you get is the Meyer-Kelly equation. Now, a modification of this, you can find out actually the delta Cp. So I have an example of a delta, like a very general delta Cp equation. So any delta Cp equation will have something like this, okay? Some variable and combinations of variables and constants to form a polynomial equation, okay? So please don't be intimidated by the complexity of this, because I'm not asking you to do anything with it. I'm just telling you. So if you want to use this Kirchhoff equation, how are you going to use it? Now, if you want to say this is 298 Kelvin and this is say 273 Kelvin, and you want to find out the delta H of that reaction, what you will need is this delta Cp. The experimenter has to provide you with this delta Cp. Now, you see this delta Cp is a function of temperature. Now, once you have this delta Cp substituted as a function of temperature, this integration becomes easy, right? Because everything comes in terms of a temperature, the T, and then you can solve this equation, right? But in order to solve this, you first have to get this delta Cp, okay? So this is how you do theoretical and experimental stuff together to actually get the difference between the enthalpies at the change in enthalpies between two temperatures. Now, what if this equation is not available, the Cp versus T equation is not available? Then you can simplify this equation, and the simplification would be that you only have the Cp at a particular temperature. So you can use that single value and you can calculate the delta H2 minus delta HT1, but it will have some errors in it. And as long as the product of Cp dt, as long as the product of delta Cp and delta T is less than the value of the delta H's, as long as the Cp dt is less than the H values, you will be able to find out this. But if this value is a large value for the range of temperatures that you are looking, so if there's a small range in temperatures and this is not a big contribution to the, and this is like really small than the H, then you can simplify this equation, right? But if not, you'll have to go through the whole process to calculate this. So this equation is important. Okay. And we give this number 32. So this is the equation that will be used to calculate the enthalpy change between two temperatures if we have delta Cp as a function of temperature. Okay. Now, similar to this, what we did here, it was we took the delta T towards the other side and we integrated. We can do the same thing when we have the same equation opened up in terms of this VI CPI, right? So what we'll just do is do a similar thing like we did in here. We will do this, but we will take the integral sign to the other side, right? And we will, and this is for the product minus CPI dt for the reactants, right? And we will integrate it similarly as we integrated here from delta HT1 to delta HT2, and we integrate it from T1 to T2, and here T1 to T2. Okay? Now we can simplify things in here. This takes becomes similar to this, and this becomes delta HT2 minus delta HT1. This VI is a constant, right? So this comes out, and this gets something like okay, for the product minus the reactants, T1, T2, T1, T2. Now, if you remember, this thing Cp dt is basically delta H, right? We have written in here. So, you know, if you get this dt towards this side, so this becomes Cp dt, and this is basically dH, right? So we'll be using that to simplify this. So this part becomes H, right? So simplifying, this remains the same, so I'm not writing that. So this becomes summation of Vi times dH, right, from T1 to T2, like delta H is going from T1 to T2, right? So from H1, because you changed it from, the variable changed from T to H, so the limits changed from H1, from T1 to HT1, okay? This is still for the products. Similar thing is happening here. HT1, HT2, and from DH. This is for the reactants, okay? So now, this becomes summation of VI. If you integrate this, what this becomes is HT2, delta HT2 minus HT1, okay, for the products minus VI HT2 minus HT1 for the reactants, okay? So this equation is basically giving you the value of HT2 minus delta HT1, okay? So I'll just simplify it, write down separately so that this is much more clearer. So this remains on this, this is the same thing. This becomes VI times HT2 minus HT1 for the products minus VI HT2 minus HT1 for the reactants. So this equation is similar to this. If you have the dependence of Cp with T, then you use this one to find out the difference between HT2 and delta HT2 and delta HT1. But if you don't, then how do you do it? Then you do with this. If you do not have the Cp, you use this, okay? So I'll name this this equation as equation 34, okay? Awesome.